Thank you so much. And I will talk about mainly about a joint work with Yael Kalai and Ron Rothblum, who are both in the audience. And this will be, this is a work about delegation of computation that has become a central problem in modern cryptography since the amazing paper of Shafi Goldwasser, Yael Kalai, and Guy Rothblum. So what is delegation of computation? So suppose that Alice has some input x in 0, 1 to the n, and Alice needs to compute some function f of x, where f is publicly known, everybody knows f, and Alice doesn't have sufficient computational power to compute f of x. But Bob has sufficient computational power, and Bob offers to compute f of x for Alice. So there is no problem. Alice sends x to Bob. Bob sends back f of x to Alice, and everybody is happy. And such an interaction occurs today a lot. There are cloud services that offer to do all your computation for you. You just have to send the input, and the cloud does the computation. It can be that Alice is some relatively weak computer that wants to delegate the computation to the cloud, or a weak device like a cell phone that wants to save on battery time and send and delegate the computation to some cloud service. But what if Alice doesn't trust Bob? So you know that the cloud service might be malicious, or even if it's not malicious, maybe they have bugs, maybe they have viruses. And the question is, if there is a way for Bob to convince Alice that the computation was done correctly, assuming that Alice doesn't have sufficient computational power to perform the computation by herself. And this is the problem of delegation of computation. And the main thing that I will talk about today is a joint work with Yael Kalai and Ron Rothblum, in which we suggest a way to do that by a one-round protocol using under standard cryptographic assumption. So the protocol is more or less of the following form. Alice, together with the input x, Alice also sends a short message u, which is kind of like a challenge to Bob. And Bob sends back together with the output f of x a short certificate w that certify the computation, that is kind of a proof that the computation was done correctly. And after this interaction, Alice is convinced that the computation was done correctly. So the parameters here are important. If f is any computation that can be done in time t, this is the time that takes to do the original computation, and let's assume that t is larger than n, the size of the input, the length of both u and w is polylogarithmic in t, so it's extremely small compared to the time that takes to do the computation t. The running time of Alice is n times polylog t, so it's essentially linear, a little bit more than linear, and so polylogarithmic in t more than linear. The running time of Bob in our result is polynomial in t. It was actually improved to almost linear in t by Holmgren and Rothblum. So this is our main result. I just have to say that there is lots of works about delegation of computation. It's a central problem with many works, many were before our work and many subsequent work to our work. Yael will talk about lots of these works, mainly about the follow-up works. I just want to mention few works. So already by the result of Kilian and Mikali from many years ago, one can give very good two-round 4 messages protocol for delegation of computation. There were also results about the delegation of computation with information theoretic soundness rather than soundness under cryptographic assumptions, which we do. And these are two of real beautiful results by Goldwasser, Kalai-R-Rothblum, and Reingold, Rothblum, and Rothblum. And as I said, there are many follow-up works that kind of build on our construction, and Yael will tell about many of these works, about some of these works. Okay, so this is this was our main motivation and our main result, but actually most of the work is about multi-prover interactive proofs and PCPs. And I want to tell you about this part, and let me first remind you about multi-prover interactive proofs. And I will do that using a metaphor of delegation of computation to the Martians. So let me tell you about the Martians. The Martians are amazing engineers. A quantum computer was built in their prehistory, and you can see that in this evidence. And in kindergarten, they build iPhones, but then in elementary school, they moved to Android. And some time ago, a group of their best engineers from the Martian Institute of Technology, the MIT, built the most amazing computer of all times. They call it the X-Time machine, but you think of it as a computer that does any computation that you want in 1 second, like a really fast computer. And now all the Martians have this computer with them, and they can use it to do computation. And of course, us on Earth, we want to delegate. There are some computations that we want to do. We want to delegate the computation to the Martians. But of course, the problem is that we don't trust the Martians. And the question is whether there is a way for us to verify that the computation was done correctly, assuming that we don't have computational power to do the computation ourselves. So one thing that we could have done is to require the Martians to just give a mathematical proof that actually f of x is the correct answer. But the problem is that in general, if the computation is in time t of n, then the proof would be of length of roughly t of n, roughly the same length of proof as the time that it takes to do the computation, so we didn't get anything out of that. And the question is if there is a way for the Martians to prove something much faster than t of n, if there is a way for us to verify their computation. And people thought about this problem for a long time and came up with some amazing ways to do that in certain cases. And one idea was the idea of interactive proofs. And in this idea, the proof is interactive. There is a prover and a verifier. The verifier asks the prover questions, and by asking questions, the process of verifying becomes more efficient. So there are very interesting results about interactive proofs that I guess you all or many of you know. But this is not what we will use here. But what we will need for our result is the model of multi-prover interactive proof. Two-prover interactive proofs. Actually, we use multi-prover interactive proofs. And this is a model by Ben-Or, Goldwasser, Kilian, and Wigderson. And in this model, two-prover or more than two provers that cannot interact with each other try to convince the verifier that a certain statement is correct, that a certain proof or a certain statement is correct. The verifier gets to ask questions both of the provers, and since the verifier can check consistency, the verifier can use it to verify the statement more efficiently. So more formally, this is the model of two-prover interactive proofs. Of course, can be generalized to multi-prover interactive proof. So the model is as follows. We have two provers, A and B, that claim that some statement is true, that, for example, that X is in L, the input X is in some language, satisfies some property. And the proof is kind of an interaction between the two provers and a verifier V. V sends two queries, one to each prover, one query Q to prover A and a query R to prover B. There is no interaction at all, no communication between the two provers. This is essential. And after each prover sees the query, the first prover, prover A, answers by some answer A, which is a function of Q, a function of the query. And the second prover, prover B, answers by B, which is a function of the query R. And based on Q, R, A, and B, the verifier decides whether to accept or reject the statement. So this is the interaction. This is one round two-prover interactive proofs. And what makes it a proof, what makes the proof convincing, is that we require the standard completeness and soundness for proofs. So the completeness is that if the provers are A, B are honest and behave according to the protocol, and indeed X in L, the mathematical statement, is true, then the probability that the verifier accepts is 1. And the soundness is that for any cheating provers, A star and B star, any possible provers, whatever they want to do, as long as they cannot interact, if X is not in the language, if the mathematical statement is not true, then V rejects with high probability, with probability close to 1. So this is the entire model, and what made this model so successful is that there are very strong results proved in this model, very strong results that give multi-prover interactive proofs for almost anything that we usually talk about, and this is the MIP equals NEXP result by Babai, Fortnow, and Lund. And actually, to do it in one round, you also need Feige and Lovas. And this is an informal statement of this result, and it says that any mathematical statement of length n that has a proof of length t can be verified by a two-prover interactive proof such that the running time of the verifier is a little bit more than n, almost linear, n times polylog t. So it's a little bit more than n when, so when t is exponential, it will be polynomial, it will be more than n. But anyway, this is the statement. It's the dependence on t is only polylogarithmic. And the communication is of only polylogarithmic number of bits, polylog t. So this is the MIP equals NEXP result. And using this result, we can delegate computation to the Martians. So we just take the Martians, we take two Martians in two different rooms, or on two different planets, if you want. We just have to make sure that there is no interaction between them, no communication between them, and then we can verify the computation. We, as the verifier, we just send one query to each Martian, get the answer A and B, and verify that their computation was done correctly. The running time of the verifier, again, is n polylog t, and the communication is polylog t. So this is very efficient and could, in principle be used. But meanwhile, on Earth, everybody is still frustrated. And the reason is that we only have one prover, and we don't trust it. So, for example, if you want to delegate your computation to some cloud service, you cannot tell them to run to actually run it on two different machines in two different rooms that won't interact with each other. You just have a cloud service, and we don't trust it. We don't know if they have bugs. So what do we do? We don't have two provers. We don't have multi-provers. We only have one prover. And about 20 years ago, there was an approach known as Aiello et al., but I understand that there was an earlier paper by Biel et al. So from now on, we don't say Aiello et al., say Biel et al. And so there was a suggestion of how to use cryptography to reduce the number of provers to one, back to one. And what was the suggestion? The suggestion is to use cryptography. So it's going to be sound under cryptographic assumptions and not information theoretically soundness. So this was the original protocol. So the verifier V sent Q and R to the two provers and gets as answers A and B, where A depends only on Q and B depends only on R. The suggestion was to send Q and R encrypted using what is called fully homomorphic encryption with two different keys. So there is now only one prover, and there is a verifier. The verifier chooses Q and R as before and sends the encryption of Q and the encryption of R to the prover P. But this encryption uses fully homomorphic encryption, and the mechanism of fully homomorphic encryption allows the prover to apply any function underneath the encryption, and therefore the prover can apply this A of Q underneath the encryption of Q and sends back the encryption of A to V, and apply B on the encryption of R underneath the encryption to get the encryption of B. So when the prover does that, the prover doesn't really see Q and R, but still is able to apply the encryption. Now the verifier knows the secret keys and can decrypt A and B, and then based on Q, R, A, and B, the verifier can decide whether to accept or reject the proof. So this is the suggestion, and it seems, yes?
In the two-prover, are the provers efficient?
It's true. I didn't mention that. The provers are actually efficient, but if you want them to be really efficient, you need also the PCP theorem to do that, if you want the efficiency that we need to use. Okay, so this was the suggestion, and it seems as if this should work, because when the prover answers the query Q, for example, the prover doesn't really know what is R, because R is encrypted. So it seems that this should work, and in fact, there is kind of a proof that it should work, a proof that it works. Of course, it's not, this proof is not really correct, I'm saying in advance, but the proof is more or less as follows. It says, okay, so we have this interaction, and after this interaction, the prover answers with some A and the prover answers with some encryption of some A and encryption of some B, and the verifier decrypted and got some A and B. A in general is a function of Q and R, and B is a function of Q and R. And now the not correct proof is as follows. It says, okay, so there are two possibilities. Either A depends only on Q and B depends only on R, in which we are done, in which case we are done by the soundness of the original protocol. The other possibility is that A depends on both Q and R. But if A depends on both Q and R, then conditioned on Q, A gives R gives information on A, and since information is symmetric, A gives information on R. So if we know Q, we are able to get information about R which contradicts the fully homomorphic encryption, the security of the fully homomorphic encryption. So it seems that if the prover is able to cheat in this protocol, then we are able to actually break the fully homomorphic encryption, which is a contradiction because we assume that it's secure under cryptographic assumption. So this is the proof. The proof is not correct. Actually, there was a paper by Dwork, Landberg, Naor, Nissim, and Reingold that shows weakness in this method, and that in general the method is not sound. Why it's not correct? You will see. Yeah, I will tell you. But it seems, yeah, it seems correct. That's true. So, okay, so let's finish the talk. Okay, so this is the problem. The problem is that A can depend on both Q and R as a function, but not as a random variable. For example, if it depends on an additional random string. So so this is an example. I'm not sure this is a very good example, but you will see the general thing later on. So suppose that A, B, Q, and R are all bits. And let's define A to be Q XOR R XOR Z, where Z is just a random bit, an external random bit, and B is just Z. So for example, if these are the answers, A and B, you can see that A actually depends on Q and R. You cannot define it as a function only of Q. But on the other hand, conditioned on Q, A gives no information on R, because there is a uniformly distributed random bit Z here. So this is the problem in the proof. And in general, there is a class of strategies, a class of strategies for the prover for which this proof doesn't work. The proof that I just showed doesn't work. And these are called no signaling strategies. And I will tell about them later on with more details, but I will already give you the definition what are no signaling strategies. So no signaling strategies of the prover are all the strategies. So this is just a general strategy. A is just some function of Q, R, and a shared random string Z. Shared, I mean, because it's both here and here. Actually, there is only one prover now. But A is a function of Q, R, and some random string Z. And B is also a function of Q, R, and the same random string Z. So far, this is just a general interaction. But we say that the interaction is no signaling if the following two conditions are satisfied. The first is that given Q, the random variables A and R are independent as random variables. So A doesn't give any information about R and vice versa. R doesn't give any information about A. And the second condition is for the same for R. Given R, conditioned on R, the random variables B and Q are independent as random variables. So these are no signaling strategies. And what we observed, it's actually a very really easy observation based on the proof that I just gave, is that if our multi-prover interactive proofs were sound against any no signaling strategy, then we would be able to remove the to use the approach of Aiello et al. Or Biel et al. So this is just an observation. But then when you go into the known multi-prover interactive proofs, for example, the MIP equals next result, or all the proofs that were known before our work, you see that none of them is sound against no signaling attacks. So what we had to do is to come up with multi-prover interactive proofs that were sufficiently good to what we needed, and I will tell more about that, and they were sound against no signaling strategies. So this is the main part of the work, to construct multi-prover interactive proofs, or PCPs, I will tell about it later on, with a much stronger soundness property, and the soundness is against no signaling strategies. So this is what we did. This is the hard part. And given that, we got the result about delegation of computation. Again, so it's Ellie sends X together with some short message U. Bob answers by f of X together with some short message W. And after this interaction, Ellis is convinced that actually f of X is the correct answer under cryptographic assumption, under the assumption that Bob is not able to break the fully homomorphic encryption that we use. And in this interaction, the running time of Ellis is n polylog t. The communication complexity is polylog t. So U and W is of length polylog t. The running time of Bob in our protocol, as I said, is poly t, which was improved to a little more than linear in t. And indeed, in order to do that, we need to use multi-prover interactive proofs with efficient provers, and that's what we do. So this is the main result. And what I want to do now is to tell you a little bit more about no signaling soundness. And no signaling soundness is not something that we invented. It's something that existed actually. No signaling interactions, not signaling strategies. It's something that existed in physics for a long time. No signaling soundness, it also appears in some sense in the paper that I talked about of that I mentioned of Dwork et al. But it was really defined as multi-prover interactive proofs with no signaling soundness were defined by Cleve, Hoyer, Toner, and Watrous. And just to try to understand what it means, let's go back to the multi-prover, actually two-prover interactive proofs that we talked about before, the model of BGKW. So when we had two provers, we said that the verifier sends two queries, one to each provers. The two provers sends answers A and B. And what we said that as long as the two provers cannot communicate, we are convinced that the proof is correct. Based on A, B, Q, and R, we are convinced that the proof is correct as long as the two provers cannot communicate. But in 2004, Cleve, Hoyer, Toner, and Watrous asked, didn't we forget something in this picture? And what we forgot in this picture was the quantum entanglement. So the point was that maybe the two provers cannot communicate with each other, but maybe they share entangled quantum state, and using this entangled quantum state, they are able to cheat us. And in fact, the EPR paradox by Einstein, Podolsky, and Rosen, what it says is exactly that in two-prover games, provers that share entangled quantum states sometimes can do better than classical provers, than provers that don't share entangled quantum states. So Therefore, Cleve, Hoyer, Toner, and Watrous defined two new types of soundness for multi-prover interactive proofs. The first of them was soundness against entangled strategies. Entangled strategies are strategies of the two provers that, again, cannot communicate with each other, but they can share entangled quantum states. And soundness against entangled strategies actually ensures soundness against all cheating provers that obey the law of quantum mechanics and cannot interact with each other. I won't talk about this soundness in this talk. I just want to mention that there was a sequence of pretty amazing results that actually redo all the MIP equals next result with provers, with soundness against provers that can share entangled quantum states. So they have soundness against quantum entangledness and against entangled strategies. And this is starting with Ito and Vidic that actually got the main result, but it was improved by Vidic, Natarajan and Vidic. And now this work by Natarajan and Vidic gives even more than that, but I will not talk about that. So this is soundness against entangled strategies. They also defined soundness against signaling, against no signaling strategies. And I will tell you more about that. This is actually the main point of the talk, the main topic of the talk. And if you have soundness against no signaling strategies, then you ensure soundness against all cheating provers that obey Einstein's principle that information cannot travel faster than light. So this is soundness against no signaling strategies, and no signaling soundness is stronger and harder to prove. And this is because all entangled strategies are no signaling, but not vice versa. So this is kind of the hardest soundness to prove. No signaling, yes? Counter example for what?
Know that you don't, if you have like, if you only ensure that the proof is, if it's a sound against non-signaling strategy, then you are fine. But now what if it's only fine against entangled?
Okay, so what we have is examples for games, for two-prover games, where the quantum value, the entangled value is 1, and the classical value is epsilon, for any epsilon that you want. So in a way, yes, but the question is what you mean by a proof. But if it's just two-prover game, yes. But as I said, now we have multi-prover interactive proofs for the exact same thing as classical, as with entangled soundness, with the exact same power as the ones that we had for with classical soundness. Okay, so no signaling interactions have been studied in physics for a long time. Just no signaling interactions are kind of all the strategies that cannot be used to pass information between the provers, between the players. In physics, signaling means that information was passed, that you can base a communication channel on that on these strategies. So if you insist that the answers will be transmitted immediately after the questions the questions arrived, then if you have signaling, it means that information traveled faster than light. And in physics, information cannot travel faster than light. This is a basic principle of special relativity. And this is because if information traveled faster than light, then in a different reference frame, information passed from the future to the past. And you don't want information to pass from the future to the past. So that's why it was studied for a long time. Again, this is the definition of no signaling strategies for two-prover games. For two-prover games. So it's just all the strategies where A and B depend on Q, R, and Z, such that conditioned on Q, A, and R are independent, and conditioned on R, B, and Q are independent. So this is for two-prover games. And soundness against no signaling for two-prover games would be exactly soundness against all such strategies. So for any no signaling strategies A star and B star, if X is not in L, then the probability that V rejects should be close to 1. This is for two-provers, and it can be generalized for multi-prover games. And here, the definition is as follows. If the queries are Q1 to QK, and the answers are P1 to PK, then a general strategy for the game is such that each PI depends on all the queries and an additional random string Z. And the condition that makes it no signaling is that for every subset S of provers, conditioned on Qi for I in the subset, the answers for these Qi's, Pi for I in the subset, are independent of the queries for all the other provers. So if you take a set of provers S, then if you condition on the queries to these provers, the answers of these queries are independent as random variables of the queries of all the other provers. So this is in general no signaling strategies, and soundness against no signaling strategies, just to show all the definitions, are just that for any no signaling strategies, if X is not in L, then the probability that the verifier rejects is close to 1. So this is no signaling strategies. And let me tell you a little bit about the power of no signaling strategies. So first, let's give an example. Assume that the verifier, that A and B are both bits, and the verifier only verifies that A XOR B equals some constant 0 or 1 that depends on Q and R. We have such proof systems, and actually this exact generalization, this exact example generalizes to any unique game. So suppose that this is what the verifier does. Then we can define the following strategy. A would be CQR XOR some bit Z, some random bit Z, and B would just be Z, where Z is random. So you can see that this is a no signaling strategy. You can just check. But on the other end, A XOR B is always CQR. So the verifier always accepts. So you can see a no signaling strategy that causes the verifier to always accept. And this seems like a small example, but actually it generalizes to many other games and to unique games. And in fact, many times, once you see all queries, you just take a random answers that satisfy the verifier. Many times this will be already a no signaling strategy. And in fact, this example can be generalized to all of NX, as there is a result that MIP with no signaling soundness is contained in EXP. This was a result before our work. In particular, all the multi-prover interactive proofs that we had for NEXP, there are no signaling, they don't have no signaling soundness, which means that there are no signaling strategies that break them, for which the verifier always accepts. And if you only have two provers, then no signaling strategies with multi-prover interactive proofs with soundness against no signaling strategies with only two provers are actually contained in p-space. So they have the same power as interactive proofs with only one prover. Okay, so in particular, all known protocols for MIP equal next are not sound for no signaling. So what do we prove? We prove that no signaling multi-prover interactive proofs with no signaling soundness exactly equal exp. So we actually show protocols, multi-prover interactive proofs protocols with soundness against no signaling for the entire exp, and this is more accurately the result. For any language L in time t of n, there are multi-prover interactive proofs such that the number of provers is polylogarithmic in t, the communication is polylogarithmic in t, the soundness is against no signaling strategies, the running time of v is n times polylog t, and the running time of the prover is polynomial in t. Again, this was improved to almost linear in t by Holmgren and Rothblum. We don't know. We don't know if we can do it with less than polylog. Yeah, it's a very interesting open problem. If you can do it with 3, we cannot with 2, but maybe with 3.
The polylog is really poly n, because of the effects. Polylog in t is really poly.
Yeah, polylog in t if t is x is poly n. That's all. And but you can also use it for t that is polynomial in n, or like for delegation of computation. That's what you typically do. Yes.
For n is in x, so if you have to prover n has witness.
So it doesn't work for. It doesn't work for nx or for n. So it doesn't work even for np. I mean, so it does work if you do np is in x, but it won't work with this running time for the verifier and the prover. Okay, so this is the result for multi-provers interactive proofs with no signaling soundness. And I want to tell you about the equivalent result for PCP. Actually, the way we prove this result is by switching to PCPs and proving the results for PCPs. And actually, for PCPs, there is a very nice way to state this result. And just let me remind you what is a PCP. So a PCP proof for X in L would be a proof that can be verified by a verifier by reading only a small number of its locations. For example, 3 location or a small number. It's not really important for us. And we have the standard completeness and soundness assumptions. If the proof is correct, then the probability that we accept should be 1 or close to 1. And if X is not in the language, if the statement is not correct, you want the probability that we accept to be smaller than epsilon. So this is PCP. But it's essential in actually all previous PCP's results that there is some proof that is written and you always query the same proof. Now, what would be no signaling strategies for PCPs? So no signaling strategies would be strategies as follow. For every subset S, think of it as a set of queries. Every subset S of locations, think of it as a set of queries. S is smaller, the size of S is smaller than some parameter K. We have a distribution AS, a distribution of outputs, of possible outputs for these queries. And these distributions are different for every S, we have some distribution A of S. Now, if V queries locations Q1 to QD, Q1 to QD is the set S. If V queries the set S of locations, then the answers are given by taking some sample from this distribution AS. So, and for every S there is a different AS, but the only requirement is that for every two sets of locations, S1 and S2, AS1 and AS2, the marginals of AS1 and AS2 agree on the intersection. So you have kind of a different distribution for every set of location, but you must always, every two of them must agree on the intersection. But otherwise, they can be arbitrary. And soundness against no signaling means that for any no signaling strategies, if X is not in the language, if the statement is not correct, then V rejects with high probability. So this is a much harder soundness property to satisfy. And the result is translated to PCP with no signaling hardness, that for any language L in deterministic time T of n, so now it's not for NP anymore, it's only for deterministic, I'm saying deterministic, it can be also probabilistic, but not non-deterministic. Any L in time T of n, we have PCPs such that the length of the PCP is polynomial in T. The running time of the prover is also polynomial in T. Again, this was improved to a little bit more than linear in T. The running time of the verifier is a little bit more than n times polylog T. The number of queries is polylogarithmic in T. The completeness is 1. The soundness is against no signaling strategies. No signaling strategies might remind some of you of Sherali-Adams relaxations because it's very similar. Let me tell you now a little bit about an application of this result for hardness of approximation, actually p-hardness of approximation. This is a result with Yael Kalai and Oded Regev. So what is linear programming? In linear programming, you want to maximize some linear function c times x under the constraint ax smaller equals b, so in some polytope. So the maximization is over x. X is in Rn, but it's bounded to be in some polytope ax smaller equal b, and without loss of generality, we can assume that all coordinates of x are larger than 0. This is without loss of generality. I want to also assume that all coordinates of C are also larger equal 0. The C times x, some Ci xi, is larger than 0. I want to actually ensure that because we want to talk about hardness of approximation. And if this function Cx sometimes is negative and sometimes it's positive, then it makes less sense to talk about hardness of approximation. Also, I'm talking here about lower bounds, so if I restrict the problem, it only makes the lower bound stronger, so it's okay to restrict the problem. But anyway, this is the only assumption that is not kind of standard in linear programming, that C is larger equals 0. Now, it has been known for a long time that linear programming is p-complete, actually that it is even approximating linear programming is p-complete. And the way the standard proof goes is that you take a circuit and you encode the circuit into the constraints, into the constraint ax smaller equal b. So you get a different polytope for every input. And what we do, what we prove, and this is the work with Yael and Oded Regev, we do a reduction to what we saw before, and we prove that linear programming is quasi-p hard to approximate, even when the polytope is fixed. So even when you have a fixed polytope, actually it's the Sherali-Adams polytope, even if you have this fixed polytope and you want to approximate linear programming, then it's quasi-p complete. So it's
fixed polytope. So what can you change?
Just the objective function. Just the C, just the objective function. So you have a fixed polytope, and you have you take the objective function and you change it, and then you want to maximize, and it's hard to separate between epsilon and 1 minus epsilon even. We can talk about it. No, I will not talk about it, but it's basically the polytope where this works. It's studied for relaxations of SDP.
So why can't you get it by using a universal circuit with the previous result?
It doesn't work. The proof doesn't work. You can actually using one thing that I require that C is always larger than 0. So you can actually get a fixed polytope, but without this requirement, which makes much less sense to talk about hardness of approximation. I just want to say that this is kind of quasi-p. So our reduction is not polylogarithm, not in log space, but in quasi-log space. There is a different way to see this result, a different way to think about
Quasi-log space or quasi-log time?
quasi-log space. The reduction is in quasi-log space, yes. There is a different way to see this result, and you can think of it as you have the Sherali-Adams polytope, and then you get some direction in Rn, and you want to say what is the width of the polytope in that direction. So that problem is quasi-p-hard. It's actually p-hard under quasi-log space reductions. And it's even hard to approximate. It's even hard to tell if the width is, you know that the width is either larger than 1 minus epsilon or smaller than epsilon, and it's still hard to tell between them. So you can actually base a computer on that. You take the Sherali-Adams polytope in Rn, and then when you get a language and an input, you just rotate this polytope according to the direction that you want, and you have like a slit of width a half, and you try to pass the polytope into the slit. If you passed, then X is in L. If you didn't pass, then X is not in L. Okay, thank you. Yes.
So you mentioned that the first person went to this ILO system. So is it that
Yael is better qualified to answer this question.
So can you construct an attack on the ILO system?
Yes.
And how do you do that?
As a result of that effect, I'll mention it later.
So you need like a specific FAQ.
Yeah, there is a result of that. This is specific FAQ.
And so it can be the case that on a certain FAQ scheme, the system will
But maybe for some other scheme. Yes.
So he's open about whether if he's only there's only so that this may shift and lie maybe
I don't know any relation, but we can think about it.
it's not known to be
Yeah, I don't know of a relation between our work and this problem.
Any more questions? Okay, so let's take one.